Well, good evening, everyone, and I am Sandy Shallis. And guess what? Tonight, I am basically saying hello and goodbye. It's the show of Jennifer and Jim. Jennifer, our wonderful hostess and climate change and methane researcher, and Jim Massa, who is an oceanographer. You've got a good packed night, and I'm going to put myself down. And Jennifer, just you know where I'll be.
Okay, guys. Well, we're so happy to have you with us tonight. We've got a pretty action packed show. You'll notice a theme right away. The theme basically is methane and heat and the Arctic. So, pretty hot topic, no pun intended. And Jim is going to start us off tonight with a very lengthy and scholarly article from Science Direct. And the title of the article is Estimation of CH4 Emissions from the East Siberian Arctic Shelf based on atmospheric observations aboard the RV Mirai during fall cruises from 2012 to 2017. So Jim is going to go ahead and dive into that. Then we've got an article from the Siberian Times, also about methane. And this just came out Thursday, November 26th. So I guess today, right? Bubbling methane craters and super seeps. Is this the worrying new face of the undersea Arctic? So this is what we've been talking about for years. We've also got something from Yale Climate 360 at Yale EDU, and this came out just a couple days ago, also about the Arctic. Record-shattering warmth pushes Arctic temperatures to 12 degrees Fahrenheit above normal, complete with graphics. And then I guess we'll discuss the latest tweets in Zach Labeland and any other things that happen to come up. So with that, Sandy and Jim, I'm so happy to be here with you tonight. Jim, would you like to start us off with this? Yeah, Jim?
I sure will. Thank you, Jennifer. Thank you, Sandy. So, as Jennifer already stated, this is a paper that just came out about a month or so ago in Science Direct. It's a study conducted by Japanese scientists, and the lead author is Yasunori Toshima, along with colleagues. I won't read through all the name there, but it's quite a large team here. I'm not going to go through the entire article because it is lengthy and a lot of it explains the methodology, but there are certain things that I wish to point out that will be the basis for our discussion. So let me start with the abstract. Abstract, of course, is the summation of the study. So I'll just read it here. Atmospheric, Sandy, is that article up on the screen? So atmospheric
Yes, it
methane
is.
mole fractions were observed aboard the research vessel Mirai sailing in waters off Alaska in the Arctic Ocean in September 2012 to 2017 to investigate the methane emissions from the surrounding region, especially from the East Siberian Arctic Shelf, known as ESAS. Now, a quick word, September is considered to be the oceanic summer. So that's when sea ice is at a minimum. The synoptic scale increases of methane were compared with simulated increases based on a Lagrangian particle dispersion model and monthly methane flux maps determined by a global atmospheric inversion system. There were good agreements between the observed and simulated methane increases, suggesting the validity of methane fluxes from the surrounding areas of the cruise experiments. The methane emissions from the ESAS in September were further optimized in order to minimize the root mean square of the differences between the observed and simulated methane increases. Okay, let me pause there for a moment. Root mean square is a statistical measurement Most of you are familiar with how to find the mean. You simply take your observations, you sum them up, and then you divide by the number of observations, and that gives you your mean. The root mean square, sometimes called a quadratic mean, is you take the observations, you square them, then you sum them up, then you divide by n, and then you take the square root. And that gives you a measurement. And that's used in a lot of situations where you're in something like this, where you're having discrete measurements and you're trying to get an idea of flux and that kind of stuff. And flux in physics terms refers to how much of a material in a concentration moves past a certain point per unit time. So you might have, say, grams of nitrate per cubic meter per second. That would be an example of a flux. So let's see. So where was that? So the average plus or minus 1 sigma, which is standard deviation, of the resulting emission rates was 0.58 plus or minus 0.47 Tg CH4 YR to the minus 1. Tg is teragrams. Tera, the prefix is 10 to the positive 12. So we have 10 to the 12 grams methane, and the YR minus 1 means per year, which was much smaller than previously reported estimates. The individual optimized methane emissions varied from minus 0.1 plus or minus 0.3, which is a wide range, to 1.3 plus or minus 0.4 teragrams of methane per year, showing a positive correlation with the sea surface temperature, negative correlation with the ice concentration. Basically, what they're saying there is increase the sea surface temperature, emissions are going to increase. Start putting ice formation in there, the emissions decrease. This is the summation of that. These results suggest a possible enhancement of the methane emissions from the ESAS in a warmer future. Now, that is a key statement right there, in a warmer future, because that is what ties in to Shakova and Smelotov's hypothesis when they talk about the potential of a methane time bomb. They're saying that the emissions are going to increase, and most likely increase dramatically, as things warm. So even though they're reporting low amounts of actually emissions, they are basically saying that, yes, this would agree with the hypothesis of Shakova and Smeletov. So then they go into the introduction, and I'm not going to read through all of it here, but obviously the Arctic is considered to be vulnerable to global warming, which could potentially enhance emissions of greenhouse gases, including CO2, CH4, and now N2O. Let's not forget about N2O also being released as the permafrost thaws. Among the potential methane sources in the Arctic region, the East Siberian Arctic Shelf might be an example of the increasing global warming-induced emission sources, and he's citing Shakova et al. In 2015. The ESAS submerged in a Holocene, some 19 to 7,000 years ago, is the broadest and shallowest continental shelf in the world ocean, including the Laptev Sea, with a total area of 0.5 times 10 to the 6 square kilometers, basically about 500,000 square kilometers, and a mean depth of 48 meters. The East Siberian Sea, with a total area of 1 million square kilometers and mean depth of 58 meters, according to Jacobson in 2002. So next thing I want to it is considered that methane was released from the degradation of permafrost and decomposition of methane hydrate under the seabed. This, and he cites Shakova, 3 papers, 2010, 2014, 2015. 2010 is the important paper of Shakova, where they posited their hypothesis, and they've been since working on that since. From the measurements of the dissolved methane concentration in the surface water, Shakova et al. In 2010 estimated the methane emission rate from the ESAS to the atmosphere to be 8 teragrams methane per year. It then was revised upward to 17 teragrams per year by refining the bubble-induced methane flux from hotspots, basically a refinement of the measurements and sampling. And considering the influence of the weather conditions on methane emissions, again, Shakova in 2014. So they are citing Shakova's research quite a bit because they've been kind of the one leading the charge on this. So then they cite Verchet et al. In 2016 constrained the methane emission rates by using remote atmospheric methane observation data and an atmospheric transport model. I will have more to say about using satellites in a moment. The resulting range of the annual methane emissions was from 0 to 4.5 teragrams methane per year. So we've seen a wide range of values being measured, reported, and so on. So obviously it's suggesting some refinements are required or needed in order to better get a handle on what's going on. So in the next section here, they talk about, the crews and so on. And if you can scroll down into where it says figure 1. Figure 1, you should see all the light blue there. The light blue is where their cruises, where they went on their research cruise collecting samples. As you can see, it's not quite in the ESAS. Now, this is a Japanese research team, so I don't know if it was an issue of getting proper permitting from the Russian government. I don't know why, but that's really sampling more the Chukchi Sea and into the Bering Strait. Just saying. And then table 1 gives a summation of the cruises, the lat lons that they went sailing on, and the range of methane in the Arctic area given in parts per billion. So then they go into a very lengthy discussion of the analytical machinery and how they, took the samples and stuff like that. That's extremely technical. It's really not germane to the discussion at the moment, but they know what they're doing, and and so on. So what I want, then they talk about what they computed and this, that, and the other thing in the results. So let's go at the results here. You scroll down to figure 4. It shows basically in weekly, it's kind of hard to read the dates, but if you look at the top left, that's from 2012. It's starting on September 12th, and then 7 days later on the 19th and the 26th, and then ending on October 3rd. And what they're looking at is the change in the methane given in parts per billion. And we're seeing, if you look at it, we're seeing spikes. Spikes is reflecting, measuring some of the releases of the methane from below. And so that's what they're showing in these. If you go to the upper right, that's for 2013, starting at the end of August, and then 2014, 2016, 27, and 2018. There's no 2015 because you look at the table above, the equipment malfunctioned, and they basically lost all the data, and we're not able to take data. So I want to look at figure 6. This to me is a nice summation of what's going on. Figure 6 shows the contribution from the various aspects of the Arctic region. The red is the ESAS. The I guess orange is Europe. The what's that, burnt yellow, whatever. The one that says West Siberia. Then green is East Siberia. The purplish is Alaska. The light blue is the Arctic Ocean. The dark blue is Canada, and then the gray is the rest. So this is showing relative contributions. Look at how much is coming from Alaska. And what's interesting, if you look at MR16, there's quite a contribution coming from Siberia.
Jim, I think we lost your audio and we've had problems. Jim, we lost your audio. Can I hear you? Hello? I don't know what happened to your audio. Jennifer's internet went down and Jim's audio. Okay, she's calling back. She's calling back. Great. Hi, Jen.
Hi
Well,
there.
now we lost Jim's audio, so he's going to have to call back. Alaska, get out and come back in. We went
Well,
through
we
that
can.
whole. He went through that whole article. That was.
Did he really?
Yeah, but I think I screwed up at the end. I was trying really hard to get the right. Okay, he's back. I was trying really hard to get the right graphs up. Jim.
Okay,
Okay, we
can
can
you
hear
hear
you.
me?
Yeah, I
So
was
how
trying
long ago did
hard.
my audio go down?
It wasn't that long, and pretty much you're done. That's a long one. You did really well on that. I think I might have screwed up the graphics. I kept going down. I kept scrolling. I hope I didn't, but they can see. People will be able to read this.
Okay, so
Okay, so
there's a, let me see if there was, I think there was one little part of the discussion. They're basically saying that they're thinking the 4.5 teragrams is more likely what's being released. So what are some of the points here? Let me start with the satellite. The satellites that sample are not geodesic. They're not fixed over a point. So you're not getting continual read. So it's always orbiting. And when it comes over that spot of the planet's surface, the instruments are aim at the surface to get the measurements. So in other words, you're going to miss a lot, especially when you're trying to capture methane releases. You're going to miss a lot. It's not like sending the satellite to look at how much the extent of the sea ice. It's there. You can measure that. You get a pretty good idea of it. But you're moving the satellite over, you're hoping to catch that time when there's a methane release. So you could miss a lot of it. If you look at the figure showing their cruises, over the years, they covered very well the Chukchi Sea, but they didn't really get into the ESAS per se. So they're trying to extrapolate over to the ESAS. I think it's a bit of a stretch. But again, when you're trying to do sampling, and they stated in their methodology, they're doing continuous sampling along the transects that they're sailing on, which is great. The ocean's kind of a big place. You're going to miss a lot anyway. So what they try to do is they collect the samples, they try to average it out. That's that root mean square that I mentioned earlier. They try to average that out, and then they try to extrapolate to the area in question. There's a lot of error that can be that can happen as a result. A lot of error. So a lot of the focus seems to be on the ESAS, understandably. But when they say that, it's not releasing that much, and therefore the methane time bomb is not a concern, well, there's the entire Arctic region. There's the Siberian landmass. We've got Siberia exploding. There is a lot that's being missed and not being measured. So my view is that these measurements are actually underestimations. And it could be underestimations by at least a good order, or maybe two. That might be a bit a stretch, but it's at least a good order of magnitude. Now, other people critique saying, well, compared to, everything else, which is say 600 teragrams per year of methane being released, this is a drop in the bucket. And they're referring to rice paddies, agriculture, fracking, which is a major contributor. Still does not mean you discount what's happening in the Arctic. As I said, I think these are underestimations. Shakova and Smelatov have, I think, adjusted their readings to account for the underestimation. And I think their measurements are closer to what is actually going on. And we're now seeing more and more releases. The releases are increasing with every year. And as we've discussed before, the question is, does it get released in little by little or massive pulses? That's a question remain. But to say there's not much methane in the ground is, I don't think, the correct statement to take. There's a lot of methane in the ground tied up in the permafrost, the clathrates, the hydrates, etc. So that's kind of my take. Some of the critique I have, satellites miss a lot. You can do all the detailed cruises you want, but you're on a little transect, you're going to miss a lot as well. So there. Sandy, I'm not hearing you.
It's a great segue for Jen to go into the Siberian Times, and which is a really cool article that is also talking about bubbling methane craters. And I am leaving.
Take it away, Jennifer.
She might be frozen. We're having a heck of a night tonight. Her internet went out earlier, so she's going to go back out and come in. This is nothing to do with me. It is like weird at other places. I did a speed test, so hey everybody out there in the chat until Jen comes back. At least she had a nice smile. Hi Jean. Hi Rich. I know I was muted because I didn't pay attention. Which was stupid. Hi, Kevin Hester. What the fuck happened to the precautionary principle? Peter Wadhams commented on a Facebook post of mine, not 50 gigs of methane, hundreds. Until Jennifer comes back, Jim. Oh, dramatic. I can't hear him. Oh, her internet.
Well, that kind of ties into the point I was just saying, that right now the estimations are underestimates, of what's being released, especially looking at the cruise data and so on. I think they're being underestimated, which, let's face it, scientists do tend to caution, they tend to err on the side of caution, and they tend to underestimate. And now we're learning that that's been a mistake, that the increases are not linear, they're exponential, and we've been massively underreporting what's going on. So we're having to adjust things. And so if the warming is increasing exponentially, which it is, guess what? So will the methane releases. And we're already seeing the methane releases increasing with every passing year. So this is going to be significant. It really is. And, you look at the landmass of Siberia across into Alaska and Canada, the boreal permafrost is a loads and loads of methane just stored in the soil, that when it gets released, it will be a significant contributor. There's just no bones about it. We can argue about what the level is. It's still going to contribute, because methane is more powerful greenhouse gas than CO2. May not linger as long in the atmosphere, but it's going to be continually replenished, and even replenished more so. It's going to have a higher warming effect.
I hear you. I was just chatting with Jennifer, and she has reappearing and disappearing internet. I hope she comes back to finish. I don't know. She's having. I don't understand what goes on, and there's storms here or there. Well, there's a storm here, but it's not here. But we can start. And hi, Hoople's cat. NOAA has it rising, but no sign of an additional spike. I'm a sweet leaf says I.
Well, the question I have for that is, when was the sample taken? How was it measured? It goes, so there are a lot of different parameters that can affect the measurement.
Yeah.
That's all. It's a cautionary note. Let's just put it that way. Satellites can miss stuff. Cruises can miss sampling.
Well, guess what? Jennifer's here, and we are going
And Jennifer
for that.
needs to jump into the methane article.
Yeah, because
Oh, you
this
betcha,
article
baby.
is a good one, and I'm going to get out of here. And
Yeah.
Jennifer, you take it. And let's hope your internet stays. Take it
Yeah.
away, Ms. Jen. This is a good one.
Yeah. So Sandy, I was thinking of doing the Yale Climate 360 article with the record shattering warmth pushes Arctic temperatures.
Okay, you got
Is
it.
that
It's
the
up.
one that you were thinking of? Okay, cool.
Whatever your
All
little
right.
heart desires. I'm out of here.
Cool. All right. So this is a very good article and not too long. So I'm actually just going to read the whole thing just very quickly, and then we're going to have some discussion about it because the Arctic is really, really hot. And this is having huge consequences very quickly in a sort of exponential fashion. So here goes, guys. Hang with me for the next couple minutes, and then we'll have a lively discussion. And there's some good graphics as well. Record-shattering warmth pushes Arctic temperatures to 12 degrees Fahrenheit above normal. Even as winter darkness descends across the Arctic, a year of record-breaking heat continues. Temperatures last weekend across the entire Arctic basin hit 12 degrees Fahrenheit above normal. Scientists announced with some areas measuring as high as 30 degrees Fahrenheit or more above the norm. These extraordinary temperatures come on the heels of an exceptionally warm summer and fall in the Arctic that saw temperatures exceed 100 degrees Fahrenheit above the Arctic Circle in Siberia and cause an unprecedented delay in the Arctic Ocean refreezing this autumn. Indeed, the Northeast Passage along the Siberian coast remained navigable this year for a record 112 days until the route finally froze over earlier this month. That 112-degree day span that 112-day span shattered the previous record by about a month. Satellite measurements show that the extent of the ice covering the Arctic Ocean was the lowest ever recorded in October. That followed a September in the Arctic in which the sea ice minimum was on the second lowest record since the satellite monitoring began in 1979. Scientists say the strongest warming now occurring in the Arctic, a region heating up 3 times faster than the rest of the planet, is in the fall. That's because rapidly disappearing sea ice, the volume of which has decreased by 2/3 in the past 40 years, is enabling the dark waters of the Arctic Ocean to absorb heat in the summer and then radiate it back into the atmosphere until deep into the fall. Speaking of the exceptionally warm conditions this autumn, Zach Labe, our favorite, an Arctic climate specialist at Colorado State University, said, there is still a large area of open water that would normally be sea ice covered. The Arctic has transitioned from a state of old and thick sea ice to one with thin first-year ice accompanied by rapidly warming ocean and air temperatures. Researchers say that Siberia's extreme heat in 2020 would have been effectively impossible without human-caused climate change and was made at least 600 times more likely by human emissions of greenhouse gases. So this is just incredible. As we discussed on Sunday, there's a blister of heat this is a temperature anomaly map. And Sandy, maybe you can pull that up, that one at the top of the article. And they're just blisters of heat all across the Arctic. And you can see that there are 3 main regions that it seems to focus on, but clearly the Laptev Sea is really involved. It goes all the way to the North Pole, that Lena River Delta, also in the Kara Sea, and all the way actually over to the Chukchi Sea. So I'd say, Jim, the whole Arctic looks to be abnormally very hot and warm.
especially the eastern side of the Eurasian aspect of it. Well, I can't help but point out how Alaska and into the continental shield of Canada and then into some parts of Greenland is cooler than average. What that is a manifestation of is the Arctic dipole, where we have competing high and low pressure systems. So right now, it's governing that the high pressure system is warming up where we see in the ocean itself over into the Siberian landmass, and the low pressure is basically keeping things a little on the cool side on the North American continent itself. So what we're looking at there is basically the Arctic dipole in effect, which is kind of interesting.
It certainly is, and it's also interesting how much of the Arctic air mass was displaced and pushed over to both the kind of mid-Siberian area and the Canadian and northern United States, and even somewhat into Greenland. I can see that even some places in Greenland are a little bit colder than normal.
Yep.
Which is
that's
yes.
a manifestation of that Arctic dipole, where you have the air pressure system working to move the air masses around. But a point there that Zach was making, and this is probably the most dramatic change of the Arctic, is the loss of the multi-year sea ice, because when you have that open water absorbing all that sun energy, don't forget, water has a high specific heat capacity. It's going to take a long time to cool down. So that is part of the reason why we keep seeing the ice forming later and later in the year. And when it does form, it doesn't get a chance to cool down as much. So you only get 1 year ice, and then when next summer rolls around, it melts, absorbs more heat. But let's not forget the influx and contribution from the Pacific Ocean and the Atlantic Ocean. You have the warming waters moving in through the Bering Sea, coming in on the Atlantic side, moving in. It is contributing heat. So you're going to have that heat, because heat rises, you're going to have that heat moving upwards through the water column as it mixes with the Arctic Ocean water above it to also melt the ice from below. Much like what we see in Antarctica, where we have the land warming the ice from above, but then you have the warming oceanic waters melting the ice from below, and then it meets in the middle and snaps off. And then you have ice chunks. So we can't neglect the contribution from the Pacific side and the Atlantic side, bringing in those water masses.
Yeah, absolutely. And all that heat has consequences, very kind of violent consequences in some cases. I want to turn our attention to the next article from the Siberian Times. I love the Siberian Times. They're the best. You can find them at siberiantimes.com. And this is an article that just came out on the 19th of November, just a couple of days ago, and it's all about methane. Has a lot of pictures. So Sandy, I hope that you, let me just check and see. Yep, she's got it displayed. So we're going to start to talk about this, and the pictures are just stunning. So these are video and pictures from the latest research mission, and it shows gas release in the Laptev and East Siberian seas. Now look at how violently that's bubbling. So a team of 69 scientists from 10 countries documented bubble clouds rising from a depth of around 300 meters along 150 kilometers undersea slope in the Laptev Sea. And they confirmed the high methane concentrations by hundreds of onboard chemical analysis. So these are field scientists. They're out in the field seeing what's going on. It's not like a theory,
If I can make this important distinction right here, they've mentioned the slope, okay? We discussed earlier about the ESA, which is the shelf. The shelf is the gradually declining sloping down, then you go over the edge. So the slope is actually on the downside to the bottom of the ocean. So that tells us there is another source of methane that probably has not been sampled and measured, in addition to the methane everyone's sampling on over the shelf. So that tells me that there's even considerably more methane that has a potential store that can be contributing to the atmospheric input. Anyway, Jen?
Okay. Looks like Jennifer froze again. Let me do this. We'll wait till she joins us back. This is just the way it happens. Hi, everybody. Let's see what happens. Jennifer, she'll come back. She will come back. Everybody understands internet problems. Jim, I think that was pretty. Oh, she's gonna log back in. Okay, cool. So anyway, let's see what everybody has to say. We have to find a way for the majority to agree on our predicament. Exactly. And oh boy, Scott Andrews said Bloomberg had a good article today about people starting to hoard food. Oh boy, there's a lot going on. Oh my gosh. Wow. Wow. Lightning Rod, hi. Basil, hi. Kim, thank you for being here. Schutzy, they're talking about pig farts in the chat. Lots of farting. Poop poop, just like the 4th of July. Hoo hoo. Let's see. I hope she can log in again. Oh, her oh no. This is like really shitty. This stinks. Well, I will miss her if she can't get back in. Of course, it'll be horrible. But we've been on for quite a while. We've been on for half an hour. I think that what I'll do is pull up the article until she comes back, because it is beautiful. And look at that. We can go into the pictures and look. A team of 69 scientists from 10 countries. 10 countries. And really, if you just look, she's coming back. If I play a video,
Yeah, that video basically shows the methane coming up, bubbling up to the surface.
Yeah, I can play it, but nobody can hear it. But I might play with it. Welcome back, Jennifer. We are very patient with this internet shit. We all have it. It's like Jim, yeah. I remember when he kept going back out. So what I was just going to do, Jennifer, if you want to see, you tell me where to go on the article. Yeah. I was going to click and see what if I want to see if it will take forever for this. Okay, there's no audio, but just watch the pictures. Watch the pictures.
It's amazing. It's just like so much. And of course, I mean, they say, oh, well, it'll all be absorbed by the ocean. Clearly not. Right?
Look at that.
Clearly not.
Oh my gosh. I think
going
it's just
directly into the atmosphere. It's outgassing directly into the atmosphere. And that's just one small part. I mean, these deposits are vast, and they're being affected by the heat. The Arctic's been so hot. Consequently, the methane's going to it's going to melt out of its hydrate state. And it's going to come out. And they can say, "Oh well, the boogeyman's not there." No, the boogeyman's not there. But we'll see. I hope they're right. Honestly,
of course we hope they're right, but we're just bringing information that is contrary to what some say, because I think what some say is not what is, reality at times. Okay, Jennifer, tell me where to go.
Well, I think this article is pretty interesting.
Go for it.
They've got a lot of different pictures and kind of, I guess, where they went on their journeys, the research areas where they went on their vessels and took their measurements. And you can see if you go down to that map that basically has like the little arrows in the Arctic Ocean. You can kind of see where they drove, or, piloted their ship around and took various samples and tried to understand the methane emissions. And they went to the hot spots. They went to the Kara Sea, the Laptev Sea, the East Siberian Sea, and the Chukchi Sea. So,
which is
the
actually one of
four
the more
big.
extensive research cruises taken to go to hit all those major seas there. But still keep in mind that however much they're going to sample and observe. Oh, by the way, there's Igor. That's Igor Smelatop. Um,
Oh,
but
is it?
however you can sample, you're still going to miss a lot. So that means the problem is even greater than we're thinking.
Yay. Well, that's
Siren?
yeah. I have a feeling you're right. I have a feeling this problem is a lot bigger than we're thinking. And I think we're gonna be seeing the results of that. Yeah, sooner rather than later. The stuff is really starting to
These
just hit the atmosphere.
graphics are amazing.
Aren't they good? That's the Siberian Times. They do the best methane articles. And Jim, they were talking about methane craters at some
Yeah,
point
I
in
saw
one of
that.
these articles. Yeah. Do you want to talk just real briefly about methane craters, what you know about them, how big they can be, when you think these last ones went off? I know there's a bunch of them in the Barents Sea.
Yeah, well, we don't know how big they are because it's they're at depth, so it's unless you're able to send an ROV down to actually look at it, it's difficult to ascertain. You can kind of do a back estimate by seeing if all the gas were released as like an explosion, if you will, then you can estimate based on the volume and compression factors, because being at depth, what the size of the crater was. But yes, I did see that there's a whole bunch of them. And what was the term they used? Pock marking the slope itself. So it's almost like a moonscape kind of a allegory that they're using there. How much is there? We don't know. We need to get down there. We need to sample. We need to look at it and see what the. But what it is, what the article say? They're actively releasing methane. It comes down to
Mm-hmm.
how much is there and what is the rate of release, and that's true
You
anywhere
know,
in the Arctic.
in a way, those craters are not surprising because we've seen those basically like methane crater blowholes on Earth in the Yamal Peninsula and kind of up and down, but mostly on the Yamal Peninsula, I believe. And it happens under the sea as well as on terrestrial. So
Oh,
if those
I
things
agree.
go off,
I agree that it's no surprise that they're being found. It's just at this point we don't really know the size of the craters and how much methane potential they hold. I think is another good area for research.
I would say so. What an amazing
I mean,
time we live in.
when you go on the land, it's easy because you can walk up to it. You can say, okay, the diameter is this. It's you can take direct measurements when you're on the tundra. A little more difficult when you're some 300 was 100 to 300 meters down or so.
Yeah.
It's a little more difficult to get to
Yeah.
ascertain the
Maybe they
size
could
of it.
get some sort of submersible or sonar or something like that.
An ROV would be good. An ROV that can withstand the pressure. You can remote control that from a surface vessel. They're handy little things, and they
Yeah.
they can document what's going on down there. You light it up and you document, and there's you can put scales on it. You can even at some ROVs can have a sampling arm on them, so they're very handy instruments to
Right.
use. And you've seen a lot more and more oceanographers using ROVs for sampling purposes.
Yeah, no, it's fascinating. It's also fascinating that many times, historically, they're accompanied by groove marks. And the methane craters appear atop the groove marks, so that would mean that the groove mark is the glacier melting, scraping, giving way, whatever. And then a later stage of that would be the methane craters, right?
That's possible.
Methane blowing up.
Yeah,
Yeah.
yeah. It's
I have a
another likely
question.
mechanism.
Is it clathrate or hydrate?
Yes.
Hydrate
It's
is methane and water frozen together. Clathrate is more in the frozen in the soil.
Oh, is that true? I thought that
Yeah.
clathrate and hydrate were interchangeable.
Not really. Clathrate is more like methane frozen into the soil, which is different than the permafrost thawing and the bacterial action releasing methane. So, but the clathrate is methane frozen into the soil. Hydrate is methane and water frozen together as an interstitial conglomerate. So that's why when you see the hydrates melting, we get that paler color compared to the rest of the ocean, because the methane and the water mixed together, and the methane is being released from the water matrix and being held together.
Fascinating stuff. Well, Sandy, we're at about an hour. Are there some other things that you wanted to go over today? You might be muted.
I think you guys did a fabulous job. Even with the internet out, both of you, really, it was an interesting show, and I want to listen to it over again. Sometimes when you're doing the controls, you don't hear all the nuances of everything that was discussed. But you know what? We did have some Zach Labe graphs if you wanted to just pull them up really quickly. Did you want to do that? They're beautiful, Jennifer. It's just the way
let's do it.
Yeah, it's just a few minutes. I'll put them up because they really are beautiful. This guy puts so much effort. There's a Hudson Sea, but I'll start it and then you guys could see, and we'll do this. Okay. Let's get it up and look at that. Aren't they gorgeous?
Wow.
Look at that. It's just he put so much work
The
into
animations are just superb. His animations are just brilliant.
And what he does for trying to make people understand what's going on here. And he said this one is the review paper that may be of interest. So it's a paper which I am not going to click at this point. That's not, but here, Jennifer, this one. Hudson Bay sea ice. Arctic sea ice is rapidly increasing in the Hudson Bay. It's earlier than average compared to recent years. The region experienced... Oh, this is beautiful. You want to take this one, Jen?
Yeah, well, it's interesting because we were looking at those temperature anomaly maps, and we saw how there was a lot of cold air that was pushed over North America, that Arctic oscillation. And while the Arctic is hotter than normal, a lot of places in Canada, North America, colder than normal. So if you look at this, you can see that 2020 is just piping right along, don't have any abnormalities, and that is, I would say, absolutely a manifestation of the action going on in the Arctic. What do you say, Jim?
Well, when you start getting into about mid-June or so, it's pretty much tracking in with the average of the rest of the ice years. There's a little low spot, a little lower than perhaps some of the other years, but overall for the Hudson Bay, I see it kind of being in the kind of near the median for the ice extent and plotting its seasonality.
Look at the Kara sea ice.
But when you look at the Kara sea ice, that's different.
2020 is having a hard time coming along. It's stuttering, right? It's stumbling in its sea ice formation. And it
That's
was a
the
little late to start, but now it just kind of, it had a jig and a jag, and that's actually not supposed to happen that much when the
Yeah,
ice
that's
is
quite
reforming.
surprising to see that dip down, and that has to be the
Yeah.
warming atmospheric conditions doing a bit of a remelt. But I mean, it's near one of the lowest extents that we have data for the Cara. But yeah, that's seen a dip down and then start to increase slowly. That is surprising.
Yeah, it sure is.
Okay, I'm going to
And
go
then
to
you
the
had
next
the
one.
sea level
Oh,
one.
look at, oh, this is beautiful. Beautifully done. Changes in sea level height
Oh,
over the
wow.
last 3 decades observed by satellite altimeters. Oh boy, this is probably.
Look at
And he got
that.
the animation from NASA. I'm just looking forward to the post Trump NASA and EPA and Department of post Trump. I mean I can't wait to see what
Yeah.
happens. Bring climate change back to the government website.
Yeah.
Sandy, I can't quite read the scale. Is that in millimeters?
Let's see if
The
I
scale?
can make it bigger.
It'd probably be in millimeters.
Whoa!
Oh, centimeters. Holy crap. So that makes it even more dramatic, seeing that it's in centimeters and looks like it's 5, 10, and 15 on the scale. I have a hard time reading it. That is quite dramatic, people, to see that kind of a increase. Just think of the surface area of the planet. That tells you how much meltage from the various glaciers has been added to the oceanic surface.
Wow, what a
This
beautiful
is
Fascinating.
this is alarming.
This is
yeah,
fascinating.
beautifully alarming.
And it's not by any means uniform, sea level rise it's got its own topography, right?
A lot of that
Look
is,
at
will be
that.
governed by what the gyres are doing. You have the surface flows. You get some concentration. Like, for example, if you look off the east coast of North America, you see that it's a little higher there, and that's because you have what's called westward intensification, which is what part that drives the Gulf Stream. So a lot of that can be explained by what the currents and the geodesic heights of the ocean are doing.
Beautiful. I mean, his graphics are lovely. Let's see if he's got anything else we can go through for the week. I think just the no, that was November 24th, the Arctic sea ice. Although currently not a record low for the day, 216 is the lowest. The sea ice extent remains more than 2 standard deviations below average. I think that's a good way to close the show.
I really like these graphs that Zach has been creating, where he has the standard deviations included, because you can see very clearly and quickly how the current year compares to the historical record that we have.
Yeah, absolutely. It's beautiful. What do you think, Jen, on this one?
Oh, his graphs are the best, And
Yeah,
you can see, I mean, if you can you blow that Arctic sea
Yeah,
ice one
I
up?
just
Can you
did.
make it full size?
Mm-hmm. Just did. I think I did. Check it out. Did I do it? Wait,
No.
there it goes.
There we are.
Oh, there it is. Okay. Yeah. And is this extent? This is extent, isn't it?
This is the extent in million square kilometers.
Yeah. Well, we're still at the lowest extent for this time ever, since we started taking measurements. I think that's the trend that you have to notice here. It's not like hugely dramatic, but we still, we're joining back up a little bit, but we're still at the lowest extent than we've ever been for this time of year since we started taking satellite measurements in 79. So
there you go.
it's happening before our eyes. It's
Of
happening.
course.
Every year it's a little worse.
Yeah. Well, this has been a
And I
good
think
show.
at this point, we just would see the positive feedback loop really start to kick in all aspects. Sea ice loss, temperature increases, melting rates, it's just going to really start exponentiating even more so. Is how I see things going.
Well, we're happy everybody came, and namaste to you, Basil, and Hoop says Hoople's cat. Sandy should organize a doomer cruise on the new Arctic Ocean in 2021.
There you go.
Yeah, we have to
You
have a
found
boat
your new
that we'll just
career, Sandy. You could
yeah,
be
but we
like
gotta
an
paddle. We have to paddle. I'm not going in some ugly, big ass, disgusting boat. But anyway, Kim, thank you. Yep, we're
Thank
now.
you, ladies.
Everything just told me we're 10 o'clock. Thank you. I'm Sweet Leaf. It was a good show, guys. Jennifer, Jim, thank you. I can't wait to listen to it over so I can actually pay attention. It was great.
Thanks, guys.
Hey, yeah. Poppy says Doom Cruise
Thanks,
would be a
everyone. Everyone have a
doozy.
good Thanksgiving.
All right, guys. I am going to play the good night. Peace out. We're gonna do our peace out. Peace out.